Hi everyone. Before we get started here, I want to just clarify a couple of things, and I did talk about both of these things in class, but just to make sure we're all on the same page here. First of all, in this original limit definition of the derivative, there is a typo here. This limit is always evaluated as h is approaching 0, because remember, h is the distance between the 2 points, and you're trying to bring them closer together, so it makes sense that h would be approaching 0. And then the alternative limit definition, this one is used primarily for finding the derivative at a given point. And I didn't give you a point here. So we are going to, for all three of these problems, find this derivative at the point x equals 2. Okay, so really in that limit definition, everywhere we see an a, we're going to replace with a 2. Okay, so let's dive into this first function. We're looking at f of x equals negative 5x using the original limit definition. And I want to point out that one of the struggles I've been noticing is how to work with this x plus h. The way that gets plugged into your function is just like if you were plugging in any other value to the function. So if I said I'm trying to find f of 3, you would plug a 3 in for x. If I said you're trying to find f of m, you would plug m in for x. So when I'm saying f of x plus h, I'm saying take x plus h and put it in place of this x right here. Okay, and of course that's going to have to be in parentheses to really replace that x. And I'm going to get rid of that because it's going to make my picture look ugly. But now let's take a look and let's see, I need a new color. So what I'm looking at here is I'm taking the limit as h approaches 0 of the f of x plus h is going to look like this. It's going to be negative 5, and then in place of the x, I'm putting x plus h minus f of x. Now, f of x is just the negative 5x over just an h. Remember, the idea here is to take this expression and simplify it so that I can get something where that h is removed, okay, where I can get rid of that removable singularity. So if I simplify up on top, that's now going to give me negative 5x minus 5h, and then we've got a double negative there, so now I'm going to have a plus 5x over h. And then what we should notice is happening is my negative 5x and my positive 5x cancel. And then also now I have this negative 5h over h. So my h's are going to cancel. And my final answer is just a negative 5. Now really what I should do at this point, and I'm going to do it kind of off to the side here, is I should now go back and say, well, what I'm really trying to do is find the limit of this thing. And you're going to see that it's not going to matter a whole lot in this one, but I'm trying to find the limit as h approaches 0 of that negative 5. Well, remember we talked about how when you're finding a limit and it's just a whole number, that is your limit. So the answer here is just negative 5. But if we had an expression left here where it still had an h in it, this is where we would put 0 in for h and then see kind of what's left. Okay, so this right here is essentially my derivative. Okay, so I want to remind you what we just found here. We just found that this function, no matter what, no matter where we are on the function, the derivative is always negative 5. And I think if you think about that graph, that'll make sense to you. But let's go back and find the derivative specifically at x equals 2. So now I'm looking at this alternative definition. So we are finding the limit this time as x approaches 2 of f of x, so that's negative 5x, minus f of 2. Now, f of 2 means I'm putting a 2 into the function f. So negative 5 times 2 is negative 10. So I'm really putting a negative 10 here now. And now this is over x minus, well, from the formula above, it's x minus a. So we're going to say x minus 2. Okay. This is now really negative 5x plus 10 over x minus 2. And just like before, our goal is to get it to where we could plug something in for that that removable discontinuity. Right now we can't put a 2 into this function, so let's see if we can get something to cancel out. Well, up on the top there, I know I can cancel out a -5. Or I'm sorry, not cancel out, but factor out a -5. So I can say -5, and then we would have an x minus 2 left over an x minus 2. And hey, look at that. From here, we should be able to come in and cross out the x minus 2's. And as a final answer, we're left at -5. Okay. Now again, and again, in this one, it's going to look kind of ridiculous, but what we're really doing now is we're finding the limit. Sorry, I don't know why my pen size is so variable all of a sudden. As x approaches 2 of -5. And we know that answer is just -5. Okay. And that matches, I mean, that coincides with what we just found above. All right, let's take a look at this next one. So again, using the original limit definition, we're starting with the limit as h approaches 0. And we're doing f of x plus h, which means I'm taking out this x and replacing it with an x plus h. So it's going to look like 3, and then in parentheses, x plus h, and then with the plus 2 on the outside. So that right there is f of x plus h. And now we're going to subtract f of x. So f of x is just the 3x plus 2. Now pay attention to how I'm putting parentheses here, because if we're subtracting this whole expression, we want to make sure we're writing it so that everything is getting subtracted. And then on the bottom here, we're going to have just an h left over. All right, let's clean up the top there. So this is now 3x plus 3h plus 2. And now be careful over here on the right with that minus sign, because now we're going to have a minus 3x and a minus 2. That minus 2 is going to be the thing that people mistake. So if you made a mistake on this one, that's where I would check first. And then we're still over h. And now let's go through and see what can cancel. So I see a 3x and a -3x. I see a 2 and a -2. And it looks like I'm left with just a 3h. Looking at that 3h over h, my h's are going to cancel. And so my final answer here comes out to just be a 3. Okay. Which, again, this is similar to the one we did up above. What I really want to do now is find the limit of this thing as h approaches 0. This is another one that feels kind of dumb because we're finding the limit of just a constant, which is just a constant. So just like before, when I go do this next one, when I find the derivative at x equals 2, I'm expecting to find that same answer, because what we're saying right here is that the derivative is always 3, no matter where we are in the function. But let's go through the motions here. So we want to find the limit as x approaches 2 of f of x, so that's the 3x plus 2, minus f of 2. So kind of off to the side here, let's see. I just want to, so I can remind you how I'm finding this. I'm going to say f of 2 is equal to 3 times 2 plus 2. Okay, that's what I'm doing. I'm putting in the 2 to the function, and so that 6 plus 2 is 8. So when I come back down here, my f of 2 is equal to 8. And then that's going to be over x minus 2. And let me get rid of this guy because I don't want this to confuse anyone later. All right, so up top here, 2 minus 8 is -6. So I can say this is really 3x minus 6 over x minus 2. Let's factor up on top. And I end up with 3x. 3 times x minus 2 over x minus 2. Get rid of those. And final answer here is just 3. So once again, if I say, what's the limit as x approaches 2 of 3, my final answer is still just 3. So that's my derivative at 2, because up above we found that that's really the derivative everywhere. Okay, let's do a slightly more complex one. This one gets into some crazy factoring and stuff here. So f of x equals 1 minus x squared. I'm going to start again with the original limit definition. So I am doing the limit as h approaches 0 of f of x plus h. So watch what this is going to look like. 1 minus, and then in place of the x, I'm putting an x plus h, and then there's the square on the outside. So that expression that I just wrote is f of x plus h. Then we need to subtract f of x, which is the original expression, but that really needs to be in parentheses because it's more than one piece, and we want to make sure we subtract both. All over just h. Okay, so let's be careful here. This is now going to be a 1 minus, when I FOIL x plus h squared, this is what I get. And if you need to go off to the side and work this out, you can, but it's x. Now, next step would normally be a plus 2xh, but remember that we're subtracting. Remember this subtraction here is subtracting all of my FOIL pieces, right? So my next piece is going to be minus 2xh, and then I'm also going to have a minus h squared. Again, all thanks to that 1 minus sign, right? This 1 minus sign is controlling all of this. And then I have another minus sign hanging out here. Now, this I don't have to FOIL or anything, but I do just need to make sure that negative sign gets used correctly. So I have a minus 1, and then when I minus negative x squared, that really gives me plus x squared. And this whole thing will be over h. And now let's see what can clean up. I've got a 1 and a negative 1. I've got a negative x squared and a positive x squared. And that leaves me here. So when I go to divide by that h, I'm going to lose an h here and here. But then this h also cancels with the h squared, which means I just lose one of those h's. But I still have one left. So the final result of all of this simplifying is negative 2x minus h. This is where the limit part matters, because what I want to do with that expression now is I want to find the limit as h approaches 0 of that expression of negative 2x minus h. But now I'm in a place where I can actually plug that 0 in for h. And so my final answer here will just be negative 2x. Okay, and that's my derivative of this function. So now my next problem is asking me to find the derivative at x equals 2 specifically. Based on what I just found, I should be able to know what my answer should be, because this is telling me that anywhere on the function, the derivative is just negative 2x. So I'm expecting my derivative to be negative 4, because negative 2 times 2 gives me negative 4. But let's work through it and make sure that that's the answer that we get. Okay, sorry, I'm trying to give myself some space here. So this time I want to do the limit. As x approaches 2 of f of x, so 1 minus x squared, minus f of 2. Okay, so f of 2 is 1 minus 2 squared, so 1 minus 4, so that's negative 3. So I'm doing minus negative 3 all over x minus 2, because that's where I'm approaching. Okay, that minus negative 3 really becomes a plus 3. And so this expression turns into a negative x squared plus 4 over an x minus 2. Now the problem with this is that negative x squared plus 4 isn't going to factor quite the way we want it to. We want it to come out as an x minus 2 and an x plus 2, but I can only do that if I can make this sign in the middle be a subtraction. So this is where I'm going to pull out that negative 1 trick. I'm going to say negative 1 on the outside. And now this is going to be a positive x squared and a negative 4 over x minus 2, which then allows me to turn this into a negative 1 times x plus 2 times x minus 2 all over x minus 2. So all I did was factor there, difference of 2 squares. I can get rid of these guys. And so the expression I'm left with, and I'm running a little low on space here, but is this negative 1 times x plus 2. So again, the limit statement is what comes in handy here. What I want to do now is find the limit as x approaches 2 of that statement of negative 1 times x plus 2. But now I'm set to where I could actually plug this in. I could put a 2 here. So 2 plus 2 is 4, and then times negative 1, and I get my answer that I was looking for of negative 4, which again matches up with what we found on the previous problem. So I hope that helps with this process, with the plugging in the x plus h and the finding the derivatives. 2 of these were really boring derivatives, and that's okay. You are going to have some boring derivatives. We'll get into more exciting ones eventually, but I would make sure that you're really set on being able to find the derivative both in general and at a particular point. So what you're seeing there in pink is in general. What you're seeing there in purple is at a particular point. Okay, so these first 3 are in your calculator questions, and I don't really have a good way with the video tool I'm using to show you what this looks like on the calculator, but I will just remind you that when I say use your calculator, I'm talking about the n-deriv function, which can be found under the math menu. I believe it's number 8. Okay. And what you want this to look like, for example, for number 4, is you're going to make it say d over dx. Some calculators make you type in that x, some calculators don't. Then you're going to type in that function x squared plus 1. And then it's going to give you the little option for x equals something. Well, the x value we care about is x equals 2. Okay. If you're on an older calculator, remember, you're just typing in these 3 pieces of information. First, you type the function. Then you type that you're doing it in terms of x, and then you type the value of 2. Okay, so I will tell you that the answer we should get here should be a 4, I believe. Yep, should be equal to 4. Let's do the same thing here. So I would do d dx. I gotta change my pen size here. Of the function x squared plus 2x plus 1. And that is taken at the value x equals negative 3. Correct answer on that one should be a negative 4. Okay, so check it in your calculator. Make sure you're getting negative 4 out as an answer. And then this last one, we're going to do d dx of x to the 3rd power, and that is taken at the value x equals 2. And as a final answer here, let's see, I believe you should get an answer of 12. Okay, so check those ones out. Those ones are all nice continuous functions, so you don't have to worry about any of those crazy, like, does the derivative exist, does it not? So all of those should be pretty straightforward in your calculator, but if you need help with the calculator steps, please let me know in class. Okay, so 7 through 10, we're matching up some derivatives here, and I hope you're starting to see some relationships. I hope you're starting to see, like, oh, anytime the original function looks like this, the derivative looks like that. Okay? Okay, so first of all, the linear function. If I were to grab a point anywhere on this line, okay, anywhere I want, and say, I'm going to find the derivative at that point. Really all I'm finding is the slope of that line, right? Because the tangent line is the line itself, okay? And that slope is going to stay constant. So whatever number I have as a derivative down here, I would have the same derivative up top and really anywhere on the line. So my derivative is a constant numerical value. And in this case, this line has a slope of 1. So my derivative is just 1. Okay, that's with letter B. So 7 is option B. And that's why, if you look back on the previous page, that's why the first two examples we did were so boring, is they were linear functions, and linear functions have constant derivatives. Okay, so now let's look at number 8 here. Number 8, let's talk about a couple of the important things here. First of all, I have a change in direction at 0. I have a local minimum at 0. So I need a graph I need a derivative graph with a root at 0. It needs to cross the x-axis at 0. Realistically, this option D is my only one. So I'm going to tell you that this is the correct answer, that 7 goes with option D. Okay. Or I'm sorry, 8 goes with option D. A couple other things we should look for, though, here is my function is decreasing up until 0, which means my derivative should be negative, which it is. Okay, it lives on the bottom half of the graph. After 0, my function is increasing, so that's where I would expect my derivative to be positive, and that's what I'm seeing here too. Okay, and we're going to talk way more about this in class, I'm sure, but what's happening here is with a parabola, the rate of change is changing, but it's changing at a constant rate, and that's why we have a linear function for the derivative. Okay, so for number 9, what's happening here, and I might zoom in on this graph a little bit. So first of all, as we move out toward infinity, okay, what's happening is this graph is starting to flatten out. So like I have a tangent line that looks like this here, and then over here it looks just a little bit flatter. And so hopefully what you can picture is as I continue to move out towards infinity, this graph is going to continue to flatten out. Now, it's never going to go perfectly flat, right? It's never going to be horizontal, but it's going to get smaller and smaller and smaller. So if you think about what's happening there is your slopes are approaching 0. They're not touching 0 because the line's never going completely flat, but they are approaching 0. Okay, so they are getting closer and closer to 0. Think about what that looks like on a graph. If you're constantly approaching 0 but never getting there, okay? And hopefully the conclusion you should come to here is that graph A, where you have the asymptote at 0, that's what this is, okay? Now, I do want to talk about like some other properties of this graph, but this one does go with letter A. Because the other thing I want you to see is look at what happens here with the derivative. See how this derivative starts climbing towards infinity? And that's because if I zoom way in here, and really probably further in than I'm even capable of doing, but as I get closer to the axis, what's happening here is my tangent line is getting closer to being vertical. Okay, it's never actually going to go completely vertical, but it's getting closer to vertical. And that's what I'm seeing in my derivative graph, is that as I'm approaching the y-axis, as I'm going this way, my derivative value is climbing because that slope is just increasing as far as it can go without actually turning vertical. Okay, so that's why letter A, that hyperbola type graph, that is the derivative of the square root graph, which is what number 9 is looking at. And then for number 10, and you have seen this graph before, we didn't talk about what it was for at the time, but if I look at the right side of this graph, I'm going to have a really similar situation to what I had in number 7. I'm going to have just a constant derivative. And in fact, the derivative here is always going to be 1 because the slope of this part of the line is always 1. So over here, it's always going to be 1. On the left side of the graph, anywhere I go and draw a tangent line, those slopes are all going to be negative 1s. Okay? So I have a graph where I have derivatives to the right that are all 1s and derivatives to the left that are all negative 1s. And then 0, I hope you remember from our discussions, 0 would be a place that we can't take a derivative. Okay? So think about what that looks like. That's this graph letter C. Okay? And again, you've seen that graph before. right? We've worked with that graph quite a bit. So that represents the derivative of an absolute value function. Okay, so for these problems, we're looking at these functions and we're talking about where the derivative does not exist. And remember, kind of by default, the derivative almost always exists. So we need to think about places where it would not be. So for example, in this number 11, the issue that I'm seeing is this asymptote sitting in the middle of my graph. That's a discontinuity, right? And we can't differentiate if it's not continuous. So as far as values where this thing is not continuous, this is at x equals -1. And ask yourself if you understand why that asymptote is at -1. You should, okay? Because the graph is not continuous. That's all we have to say. Okay, so if the graph is not continuous, problem solved. Same thing, honestly, on number, oh, I guess I'm hopping across here, but to number 14, I've also got asymptotes running here and here. Now, this graph is numbered kind of strangely. But you should be able to look at the equation and tell me where those asymptotes are at. We have asymptotes at x equals 2 and x equals -2. And same reason, graph is not continuous in those places. Okay. X squared minus 9, but it's the absolute value of x squared minus 9. And so the issues I'm going to run into are these sharp points right here. Okay, so that I believe will be at 3 and -3 because that's where this thing would zero out. And right, that's where absolute value is going to make it change directions. So I would say x equals 3 and x equals -3. And then I would just say something along the lines of derivatives on right and left. I'm trying to shorten this up to squeeze it in this space. Don't match. Okay. Number 15, this is a square root function. And the place we're going to run into trouble here is this end point. So that would be at x equals +1. And the reason that one's a problem is the derivative does not exist to the left. So it's not continuous from the left. Okay. Okay, x minus 3 to the 2/3 power. Yeah, this is kind of a crazy one. So this point right here, and again, you might want to wrestle with how that graph is numbered for just a second. I can tell you from looking at this equation that that little pointy place is happening at x equals 3. And this is really the same reason as the one up above. So the derivative on right and left don't equal each other. They're not the same. And last one. This one really falls in line with the first couple that we did. I'm seeing a discontinuity here, right? I'm seeing a jump discontinuity at x equals 0. So I'm just going to say x equals 0 because this thing is not continuous. And that's it. That's all that one takes. Okay, this page is having you draw the derivatives of functions, and I'll be honest with you, I don't care if you draw them on the separate graphs or if you draw them right on top of the graphs that we started with. Let's see, I'm going to pick a different color here quick. Okay, so the first place I would do, or the first thing I would label is where is your derivative equal to 0? So like, for example, I see a flat tangent line here. So I'm going to mark this point as a 0. And then same thing here. I see the top of a curve. And so this point is going to be a 0 for my derivative. I'm going to get rid of these horizontal lines just because I don't want them confusing us in our drawing. But that's where they're coming from, is the fact that that's where my max and mins are. Okay. Now, I'm seeing that this section of the graph is increasing. Up until that green dot, this is increasing. So I'm expecting my derivative to live up here in positive land everywhere before that green dot. Between the green dots, my graph is decreasing. Okay, and so in between the green dots, my derivative needs to be negative. And then again, over here from this green dot to the right, this graph is increasing, so my derivative is living back in positive land. So my derivative is going to have kind of that parabola shape to it. It's going to look something like this, and I don't know how far down it's going to go, and then it's going to come back up. Okay, that's what we should be seeing here. And again, just to point out, if I were to try to identify where the inflection point is, like where from the curve changes from curving downward to curving upward, that'd probably be about here. And that lines up with the bottom of my derivative function. So the derivatives change direction at those points of inflection. Okay, let's do the same thing with the next one. So here's where my derivative is equal to 0. So I'm expecting this to be a root on my function. I'm seeing, let's see, this section of my graph is increasing, so it needs to be positive. My derivative needs to be positive to the left of this point. And then here it's decreasing, so my derivative needs to be negative to the right of this point. So I will tell you, and if you made your graph do some sort of crazy curvy thing because you just felt like it should, that's fine. But I will tell you that this graph really is just a linear function, which accomplishes what we wanted it to, right? It's positive to the right, it's negative, or I'm sorry, I said that backwards. It's positive to the left, it's negative to the right. It crosses right at 2, which is where the 0 should be. So that's what that derivative looks like. And then number 19. Number 19's got a lot going on. Let's see. So let's mark our zeros. So I'm seeing a 0 here. I'm seeing a 0 here. Seeing a 0 here. And I'm seeing, whoop, not there. Touch my pen in the wrong spot. Seeing a 0 here. Okay, so I see 1, 2, 3, 4 places this thing needs to cross. And we need to be positive over here, right? So I'm going to be up here. Then I'm going to come down. Somewhere in here, I'm going to change directions and come back up. Because everywhere to the right of this point, this is where I'm increasing. So between these two dots, my graph needs to be living up here. Okay. Once I get to this dot, and actually I sketched that incorrectly because it's going to come up, but it needs to turn around and come back down because after this point, we're living in negative territory, right? So it's going to come back down, turn upward again, so that to the right of this point, it can go up forever because that's what this is doing, is increasing forever. So let's see if we can get that. We're going to start positive. So we're going to start up here, we're going to come down, come back up, down, come back up, and then it goes up forever here. And this would actually also go up forever here as far as we know. Okay, I mean, based on the way this graph goes. And I guess really we could draw endpoints here because it looks like our graph might have endpoints. But that's what this thing should look like. And I know it's kind of a mess, but again, what I'm really looking for is, are your zeros in the right places, and is your graph positive and negative in the correct spots? Okay, last question here. We're looking at the temperature of a pot of tea over time, okay, for 10 minutes. So every so many minutes, we're measuring the temperature of this tea. And the question says, find H prime of 3.5. Well, just to remind you what that notation is saying is really it wants the derivative at 3.5, which means what is the instantaneous rate of change at 3.5 minutes, okay? Now, I'm a little bothered by the wording of this question because we can't actually find this value. We would need to have a continuous function where we actually have a function defined that we could find derivatives of, and we don't have that, but we can estimate this, okay? So 3.5 is living in between here. We can't find an instantaneous rate of change, but we can find an average rate of change around 3.5. Okay, we're going to get as close to it as we can. And with this data, this is as close as we can get. Okay, so our approximation for H prime of 3.5 would be approximately 52 minus 60 over 5 minus 2. So that's -8 over 3. Okay. And we could make this into a decimal. I think maybe that'll make the most sense here. So this would be like negative 2.6 repeating. Okay. And our label here, and for the label, it might actually be easiest to go back to this negative 8 over 3. But this is degrees, and this is minutes, right? So this is negative 2.6 degrees per minute. So when I'm being asked to interpret this in context, what does this mean is happening? This is saying that, so at 3.5 minutes, the tea is cooling at a rate of, I'm going to say 2.7 degrees per minute. Okay. Or we could even backtrack to here, and we could say this is telling us that we're losing 8 degrees every 3 minutes. Okay, that's what this can be interpreted as. But when we're talking rates, we're usually talking per unit, so per minute. Okay, so the important parts to have in here are that this is specifically at 3.5 minutes, because if we looked at some other time, we might find a different answer. This is cooling, right? It's a decrease because it's negative. And then what is that rate and what is the label on it? So the label would be degrees per minute.